Lecture 9.3, the magnetic field of a straight current carrying wire. The procedure for calculating the magnetic field using the Biot-Savart law is similar to calculating the electric field using Coulomb's law. So I want to compare the two processes. So let's compare the process of solving for fields between coulombs and the Biot-Savart. So let's say that we'll start here by listing steps. So let's say this is step one. And the first step, no matter what field we're talking about, is that what is the physics of the field before we calculate it. So that is true no matter what. So now when I go to step two here, now I'm going to start breaking it into what is the electric field and then what is the magnetic field. I'm probably going to have to adjust the margins here just to try to keep things symmetric here. So the first thing that we have to do for this here is that we have to do what? The first thing is that we have to define a charge element. Or define the charge element. dq. So I say the exact same thing for the magnetic field. The first thing we got to do for the magnetic field here is that we have to define the current element. I ds. So that would be step two right there. So then the next thing that we have to pay attention to is when we go to step three, that little dq produces a little electric field. So we need to calculate that. This little current element, IDS, produces a little field at point P. So now what we want to do is that we want to determine the little DE field produced by DQ. And ultimately, here's what we're going to get. We're going to get that our electric field is then going to be equal to 4 pi epsilon naught. And then we're going to have little dq r squared, and then we have our directional. But clearly, the most important thing here is actually calculating the the displacement vector. So now I'm going to repeat the exact same thing over here. So if I start to look at the magnetic field, what do we find here? We want to determine the little dB field produced by IDS. So in this situation, now we have a magnetic field, a little tiny magnetic field, where now we're using this relationship here. But it's the same process. So then I finally get to step 4. And now what we're interested in here is the total or the net electric field by all DQs at point P. So that means we're going to get the net field by integrating all of these DEs. And so ultimately, we have to solve this integral. I do the exact same thing for the magnetic field. We say that the net magnetic field by all current elements at point P. And then we get that net magnetic field by integrating over all of the little dB fields, which leaves us with this final integral that we have to do. So if we're looking at these guys step by step, you're actually seeing us really repeat the process of Coulomb's law. And that's what we want to do now for a wire. So I'm going to repeat this whole process, but now I'm going to get into a calculational form. So a straight current carrying wire is extremely important since all circuits have finite straight wires. So that's why it becomes so important here. So let's set up the question and then move on. So I'm going to say this. We have, so as our question, it goes something like this. A current carrying wire of length 2L carries current I. And we know that this guy has to be a constant. So then we're asking, what is the magnetic field at point P. So to visualize the magnetic field, of course, we got to sketch the situation. So we just went through the sort of like the outliner here and the outline that we just did. So now I want to repeat that process. So I want to sketch and repeat the process outlined above. So the first thing that I want to do here is that I have to define a coordinate system. Okay, so I'm going to say that the first thing here is that we want to define a coordinate system. So I'm going to say that the current is moving along one of the axes. And I know that it's a constant, so I'm going to say that it's going to move along the x direction. So the first thing that I'll do then is that I'm going to say I need to choose a coordinate system. So if I choose this guy to be my x-axis, then this will be y, and then this will be the direction of z here. So I would say that this is our first step right here. Now that I have that, now I need my wire. So I have my coordinate system. So then I'm imagining that I have this wire here. And the way I've set it up here is that I have a wire that looks something like this. And I know that I have a current moving in that direction right there. So I'm specifically saying, even though it doesn't say that, I could have done it along the z-axis or y-axis, it doesn't matter. But I'm saying that this is my x-axis right there, and that current is moving in that direction. Now what I need to do here is that I need to find out, where do I want to calculate the magnetic field? Well, we're going to need a point P, and so since symmetry typically plays a big role, I'm going to divide this wire in half, and I'm going to say that right here, I'm going to make that my origin right there. So then I'm going to pick a point P right here. So if I pick a point P here, then that means that this guy here is in the Z direction. So now I have a picture of what that wire looks like. And of course, if I'm talking about lengths here, this will then be minus L, and this would be plus L right here. So now the next thing that I want to do is that I need to divide the current into tiny current segments. So I know that I need a little piece of current to find out what that magnetic field is going to look like. So I'm going to come over here and I'm going to say, I'm going to look at this little tiny bit of current. And that little tiny piece of current, I know is moving in that direction. And I'm going to define that little tiny piece of current as IDS. And then that guy is going to be located where? It's going to be located a distance x from the origin along the x-axis here. So that's my second point right here. So then what we have to do is that we have to then go in and we have to calculate the magnitude, right? So now we want the magnitude and direction of the little dB at the point P. So when I look at that, what that really implies here is that we really got to focus on the displacement vector. So then I take my vector, my displacement vector, and I need to know what is the vector R from that little IDS to that point P. So right away, we see here that now this becomes the third thing that we've talked about. And then finally, what we're going to need here is that at that fourth point here, is that now, maybe it's just the fourth point, we now have our, we now have the little dB field at point P. So that means at this point, we now have what that magnetic field is at point 4. So now what I'd like to do is that I want to get into the details. Okay. So if I get into the details, then that means I'm going to go through that step process here. So the first step is that what is the physics of the magnetic field before we calculate it. So what I want to do is that I'm going to copy this guy right here, and I'm going to take it down with me. And what we've said already here is that we expect symmetry to play a big role. So we expect symmetry to play a role in simplifying the calculations. And we've done this numerous times already with electric fields. So to see this, raw to symmetric current elements or segments. So I just took a copy of this. So let me come in here, and then I'm going to modify this. So let's see here. I'm going to put this guy right here. So I'm going to take away some of these things here. So the one thing that I want to pay attention to here is that I want a second wire segment. And so let's say that this wire segment is symmetric with the first one. So then I'm going to call this guy 1. And then this guy, which also has a little current going in that direction here, is also going to be IDS2. So when I look at this guy has a displacement vector of R. We'll call this one R2. We'll call this guy right here R1. Now, if I look at this thing, the first thing that I want to do is that I want to apply the right-hand rule to get the direction of the magnetic field. So let's apply the right-hand rule to get the direction of dB of the wire. So remember what we have to do here is that we have to bring in our vectors and put the tails together. So look at what the first charge element is telling me. It's telling me that I have this charge element right here, which will be I ds1. Now, instead of drawing it in green, I'm going to draw it in black, but you could see here is that this is R1. Now note, R1 can be broken into parallel and anti-parallel components. So in other words, I can break this guy into here, and that's going to be R1 anti-parallel. And then I can break this guy into here, and that's going to be R1 perpendicular. And we know that this component right here is going to go to 0 when I take the cross product. So I only have two vectors. So using my right-hand rule, I see that there's going to be a contribution of the magnetic field by IDS1 that goes into the, the screen. Now, if I repeat the same process for charge element 2 here, you'll see here that I'm going to have IDS2. Now, when I look at that guy, you can see that this guy has a vector R2 in this direction, and we do the same thing. So I make a parallel component, and I make a perpendicular component. This will be R2 parallel, where again, R2 perpendicular, where R2 parallel, that is going to go away from the cross product. So I only have two vectors again. And so when I look at that magnetic field, you're going to see that this magnetic field also points into the screen. So when I'm looking at that, we know what that magnetic field is. Furthermore, they have the same magnitude of the displacement. So that means we can simplify the calculation. So the net field, or the net direction of the field, is into the screen, and they have the same magnitudes since their displacements are the same. That being the case here, we could then say that I have B net, and I have two components. I have one due to the green. I have one due to the blue. And because they have, equal magnitudes, I'm going to focus then just on dB1. But then I'm going to redefine this thing here. I'm going to come back and I'm not going to redefine it. I'm going to take back what I said. So I'm going to go, this is now this guy, and I have this as my magnitude. And according to our sign convention, remember what our sign convention is. It is this guy right here. So if I bring this down here, you'll see that the sign convention then tells me that if it's pointing into the screen and this is the positive y direction, this must be in the negative y direction. So in other words, this is what symmetry tells us about the field. So before we get started, remember, we're still trying to understand the physics of the field. Okay, so that's what symmetry is telling us. So that tells us a lot about the field. Now, is a finite wire important? Not really. So if one looks at the wiring inside your home or apartment, these are effectively infinitely long. Since the length L is much larger than the radius of the wire. In other words, L, a lot of the times, is much, much bigger than the radius. And we can, like, here's an example here. So for a 15 amp circuit in your home, and by the way, when I say 15 amp, that typically tells you about the gauge of the wire, the thickness of the wire. One uses a 14 gauge wire for lights and outlets, which have a thickness. So what I mean by thickness is that I mean the diameter of 1.628 millimeters. That's just a number that I've memorized. In physics, we don't use diameters, we use radiuses instead. So that's just a small thing. The lengths of wire inside your home vary, but are much longer than the radius at almost any point. So if I think about an image, so if you were to look inside your ceiling here, you're going to see that you typically have these wires that are clumped together and they stretch out for quite some distance, the distance across your home, for example. So if you compare, right, the length of 2 meters, which is about 6 feet, right? That's your room is typically much wider than 6 feet. So if you compare the length of 2 meters to the radius of a 14 gauge wire, the ratio shows that if I take the length over the radius, well, that's got to be, so if I take the radius, I got to divide the diameter. So that's 0.814 times 10 to the minus 3 meters over 2 meters. Guess what? That's 2,500 times larger. That is a lot larger. The wire length is 2,500 times larger than the radius. Effectively, this is an infinitely long wire. So the magnetic field of an infinite wire is more important than that of a finite wire. Unless, we need more sig figs. So when I'm thinking about what do we really want to calculate? So we are more interested in the magnetic field of an infinite wire than than the magnetic field of a finite wire. That means that when I look at the limit of L being much bigger than R of B finite, we are looking to get a good approximation to the infinite wire value. And again, we have to worry about the number of sig figs. How important are the sig figs to the measurement? In everyday situations, the infinite wire result is more than sufficient than dealing with the more complicated finite wire value. So let's look at this here. So now we have to solve the Biot-Savart law. So from the Biot-Savart law, the magnetic field requires us to calculate two things. The first one, which we've already done, is that we use the right-hand rule to determine the direction of B. So we always do that. Then we focus on the magnitude. So the magnitude, you know what? I should have put little dB, not B. So the magnitude of little dB is then going to be this here. So I'm going to write dB, and I want the magnitude of the vector. So then that means I take the magnitude of this guy here. And when I do that, the magnitude of a cross product gives us a sign factor. So I have mu naught over 4 pi. I have I ds1 times sine of theta divided into r squared. So you could see that this guy is really giving me the so-called directional. So we have to calculate this directional sine of theta. And then, of course, we need the magnitude. And all of this comes from what? The displacement vector. So then if I go through my process here, I need I ds, I need my element. I need r, and I need sine of theta. And once I have those quantities, I then get my dB value. So that's where I have to go. So now that we've studied the field, now let's go look at the details. So now we're on step 2. We need to define the current segment, the little current segment, IDS. And I think this is going to be fairly straightforward. So if we go and we get the picture of what we just calculated, let me see if I could go get the picture here real fast. Here's the picture that we had. So now if I come back over here, I'm going to put this picture right here. This is what we had right here. So now what we want to do here is that we want to modify this so that it looks exactly like what we want. I'm only going to focus on one term, right? I'm only going to focus on ds1. So I'm going to get rid of this guy right here. So I don't care about these guys. And I'm only looking at this guy right here, right? I only care about that guy. So in the end, I'll have to come back and I'll look at this guy. And we'll look at the details here. So this is what I'm looking at right here. So this is my current element right there. So the current has a constant value where I is equal to a constant. That's what we mean by magnetostatics, where all the current flows along the positive x-axis. So we can just look at this thing. If this is the x-axis right here, we could see that that guy has to do that. We see that this is located at x, and all that current element is located at that little tiny ds value. So we conclude here that I ds, well, that is a constant, so it has to be located all at dx in the x direction. That's what the current element is looking like. You know what? Let me move this. Oh, man. Here, how about if I move this over here out of the way? So if that's the case here, then if I was to look at this thing, it really says this. So physically, I said it, but I didn't write it. The tiny amount of current is contained within IDX, located at position X, will induce a tiny um, what do I call it? dB field at point P, at the observation point P. So I'm going to need this guy, so I'm going to keep copying this guy. So now that I have that, let's go to the next step. Step 3. Now we want to calculate the displacement. And of course, the displacement is a vector. So I need to talk about its magnitude and direction and the tiny field dB. So from step 1, we found that the magnetic field of the wire, the finite wire, was equal to 2 dB1 in the negative y direction, where dB1 we already found was equal to mu naught 4 pi. Then I'm going to have I ds1 times, actually we don't have to say ds1, it's not ds1, it's actually I dx times sine of theta over r squared. In other words, what we got to calculate now is the sine, is the magnitude, r, right? We need this directional, and we need that magnitude of the displacement. So let's go look at the details of that thing. So from the geometry, the displacement and directional must be calculated. So here's my wire. So if I look at this guy, I have this situation right here. So now let's go look at this guy. So the first thing that I'm going to look at is that I'm going to say, I know my current already, right? We know that IDS is located at X. And we've already written that down. Now, the next thing that I have to do here is that note that the position here, I'm going to label as Z right here. So I'm going to say that the point P is located at position Z. And then finally, we have to look at the displacement vector. So now if I look at the displacement vector, there's two parts to it. So the first part tells me that I'm going to have a displacement vector that goes like this. Going to go from here to here. So its magnitude is going to be r, but then I have to worry about the angle. The angle is between I and r. So then this angle here is the angle theta. So if I look at from the right-hand rule that we already saw before, we saw that the magnetic field at this point is then going to point into the screen. So now that I have that, I could now go in and look at the details. So I'm focusing on this triangle here. Okay, so we have to focus on that triangle. So we have to focus on the displacement triangle to calculate r and sine of theta. So if I look at that triangle, it's right in here. So if I look at this thing, I'm seeing that I'm going to have a triangle that's going to look something like this. That's going to be my distance x. Now note that this is the x-axis right in here. Now I have my displacement vector that goes from here to here. And then I have my z length right there. So this is what I have to focus on, this triangle right here. So now that I have that, note that this angle right here is theta. It's not inside the triangle. So I need to make it inside the triangle. But note that this right here is 180 degrees. So if that's theta, then this angle here must be pi minus theta. Now I can calculate these guys. So if I look at the magnitude, I could see here is that r is then going to be, from the hypotenuse rule, going to be this guy right here. Now, if I look at the directional, the angle that I have here is pi over theta, not theta. However, sine of pi minus theta is the same as sine of theta. So that is sine of theta. And so you could see here that this has to be what? The sine is the opposite side of this guy. So then that means I'm going to write the sine here is then going to be z over r, which is the same as x squared z squared square root into z. Now that I have those two, I can write out the details of the magnetic field. So writing out the details of the little B field of the wire, we then have that we have dB wire. We know this has to be 2 dB1 times sine of theta. You know, that's a mistake here. It's not sine of theta. Now I write dB. So then this will be 2 mu naught over 4 pi, and this will then be I dx sine of theta over r1, or just r squared, excuse me. So if I now put in those details here, I'm then going to get an expression that then reads 4 pi into mu naught. I'm going to get 2I dx Then I'm going to get x squared plus z squared. And then my sine term is x squared plus z squared square root all into z, which then tells me that now I have my magnetic field of the wire. It's then going to be 2 mu naught I times z divided into 4 pi, and then I have x squared z squared to the 3 halves into dx. And that's my field right there. So now we're on step 4. And what we want to do is we want to integrate all of the little dB fields. So summing over all current elements slash segments, we then find that we have B finite wire is then going to be minus L to plus L of dB wire, but because of the symmetry of the situation, we reduce this down to half of the integral, which then goes from 0 to L of x squared z squared to the 3 halves into dx. And when I compute this guy, I get an equation that then reads mu naught Iz over 4 pi. Then I'm going to get z squared L squared square root into 2L. That is, when I look at the full field of a finite wire for the coordinate system that we used, we get the value of 4 pi mu naught. I'm going to get z squared L squared square root into 2L in the direction of the negative y direction here.